So I am in PhD student and I'm working on additive manufacturing on laser power bed fusion during keyhole regime, and I will talk about today about the influence on laser parameter on the multiple morphology. So I'm working with Chris from École des Mines, but also with Enise, Mateis, and Lamcos Laboratory. So first, I work with laser powered bed fusion, which is metallic additive manufacturing process. So it's a method to produce fabricate product by a layer manner with a laser as energy sources and a power bed with a power bed. So you have many advantages to work with this process. It's a fast process. You can customize with complex geometry products. You can make also topology optimization, and it works with many material, metallic material like steel, aluminium, etc. But there are some big challenge and drawback for this process. You can create many defects as pore formation, crack formation, distortion. You have also a significant roughness of your final pieces that can be problematic. Also, you have potential post-treatment after your creation of your project as heat treatment or chemical treatments. So we have the costs of the final pieces, and also it's an expensive process. And because for powder bed fusion you use powder material, you have also a major risk of health, safety, and environment. So it's costs a lot to have protection for people who work on additive manufacturing. That's why for this moment it's also for high value added products as luxury products, aeronautic products, automotive products. So here, this is the machine that I use at Enise. It's a Pro X200 from this system company. So you have inside, so is the chamber and here the machine, and you have two parts of this machine: the laser parts, just here, and the chamber parts. So, and inside, this is a chemistry of inside the chamber. And how works the laser powder precision? So here you have the powder stock, and you have a recoater, and the recoater will spread a layer of powder on the build plates here. And after you have the laser that will sinter the powder bed to solidify the powder. And after your build plate go down, the powder platform go up, and a new layer of powder can be done. And here you make 100 layer, and you can fabricate your final pieces like this. So, and I say at the introduction, I work with keyhole regime, which is a regime really specific, and I will explain you the different steps. So first, the laser comes to hit the surface, and the powder bed absorbs the energy, and the powder will melt in and form the melt pool. The temperature near the laser is higher than on the boundary of the melt pool, so it creates a temperature gradient, which creates a surface tension gradient. So you have a monogony convection inside the melt pool. If you stay in this condition, you are in the conduction mode. But in my case, I put more energy on the laser by increase the power of the laser, for example, or diminish the scaling speed, for example. And the boiling temperature of the melt pool is reached, and you have the evaporation of the metal elements inside the melt pool. So after you can create a cavity inside the melt pool. Here. So it's the keyhole cavity. And the keyhole cavity is maintained because of recoil pressure linked with metal evaporation, but the surface tension and the hydraulic pressure tend to close the cavity. So you have many competition inside the cavity between recoil pressure that's open the keyhole and surface tension that tend to close the cavity. So it's a really unstable regime that create a lot of pore formation if you don't if you work with hard energy and you are in the cure regime. So here you can see a process window of additive manufacturing. So we find the cure regime with, as I said, with high power and low scaling speed. And here we can see here's the cavity from these two examples. On the contrary, you can find the boiling effects, which is just like a bubble of droplets of metal that is not, you have not interaction between the metal and the substrates. Also, you have the lack of fusion. I don't know what is in the picture. But you have more interaction than boiling effects, but it's not as high as the stability zone, where the dip of the melt pool is the same that the substrates on the side. And so yes, more on cure. So my purpose in this thesis is to study the interaction of laser and powder during the keyhole regime, and especially in the transition zone between keyhole and stability regime, and to see the evolution of the melt pool dynamic, and to understand the mechanisms of the keyhole pore formation in order to avoid to create pore formation during the process, or to control the porosity inside the metal. So first I will talk to you about laser analysis that I made, and after we will try to find if the laser analysis is good with experimental procedure by formation of the single track fabrication. So for laser analysis, so we back with laser ProX 200. So here you have at the beginning the laser, and here's the chamber. So we can see here's the recoater and here's the build plates. And on the build plates we put a Synology focus beam profiler in order to take a picture of the spot size to study it, to find also the form and the evolution of the spots during the fabrication, and to measure the energy density of the laser. So first, we see the evolution of the spot size as the focal point, and we try to replicate the laser during the fabrication. It's a laser on during 45 seconds, which corresponds to the centering of laser, and it's laser off for 50 seconds, which is the time for the recoater to spread the layer, the powder layer. And we can see here a huge difference between the beginning of the layer and the end of the layer, which is about 100 micrometer at the beginning and more than 200 at the end. So we also see that you reach a steady state about 3-4 layers, and we can divide this in 3 states: the cold states, which is at the really beginning of the construction, and the hot layer beginning, which is in the steady state at the beginning layer, and the hot layer end, which is in the steady state also, but at the end of the laser shot. So here it means that during the construction you have evolution of the size of the spot size, and it's caused by the focal shift. It's a well-known phenomenon in the additive manufacturing. It means that during the fabrication and during the laser suturing, the lens and the F theta lens is heated, it's deformated, and the refractive index will change, and it causes displacement and a shift of the focal shift at cold. It is here, and we see that when the lens is hot, you have a shift and it tends to go up, and the difference between the F0 and the F is named the focal shift. So we measure the focal shift here by measuring the caustic of our laser or of the laser at these three different times called beginning layer and hand layering, hot layering. So doing this, we also take picture of the laser at the different Z position, and we trace the size of the laser beam here. You see here, you can see the laser caustic evolution at 150 watts at cold states, and we added the hot layer beginning state and the hot layer end states. So we can see here that this is the waste of the laser at cold, and increase with hot states. And we also observe that it's larger at hot states than at cold states. So on this machine, on LaserProX 200 that I use, there are a significant focal shift that is measured. You can see that the focal shift is about 6 mm with at 100 watts and about 10 mm about 200 watts. So it also depends on the power that you use for the fabrication. And it's a really huge problem because also the spot size is twice high at 200 from cold state to hot state. So now we will try to fabricate some single track and to observe the phenomenon of the focal shift on the single track formation. So I use powder of stainless steel, so it's the same ProX 200, and I made some single track, so it means that I just made one track with my laser, and I try to change the density, the energy density received by the powder gun by changing the power, the scanning spin, and the spot size by modifying the distance between build plates and we measure the melt pool dimensions, those the depth, the height, and the width. So I fabricate with the three states of the lens, so called hot layer beginning and hot end beginning, with a batch of power and scanning spin. And also I modify the focal position. By modifying the position, I modify the spot size, and consequently, I modify the energy density received by the powder gun. And you have to know that the focal positions, as I said before, depend on the power laser and also on the lens states. So here are the results. One of the results from the depth of the cavity. I choose the depth of the cavity because it's the dimension of the melt pool which is the more representative of the keyhole of the keyhole. So here we can see in blue is the cold states as the focal points. Yellow is hot beginning state but as the cold focal points, and orange is the hot beginning state at the hot beginning focal point. So here you can see that finally the blue and the yellow is really close, then orange is not correlated with the blue and the orange. And here we can see here that in this example the cold states at the cold focal points is also the same that in the hot state but with cold focal point too. It means that here we can suppose that finally we don't really observe the focal shift that we measure by the laser analysis, and I choose to work with the cold caustic at 150 watts as a reference value. Nevertheless, we can say that we don't have focal shift because we say here is example with high power and high speed, and you can see here that you have a difference between the blue and the yellow states, but it's not at the orange state too, so we can say that we have a focal shift, but it's not as high as measured by the laser analysis. You have a low focal shift, but for simplifying my calculation for this moment, I choose to say that I don't have focal shift, and we are actually working to better measurement this low focal shift. To finish, I will talk about a little prediction about the form of manifold by utilize the normalized energy, which is just a link between the energy absorbed by the powder material and the energy diffused inside the material, and which is melting the powder. And here this is my results, and here this is the result about literature, and we can see that we observe the same tendency with two domains, with the keyhole domain here with slope of the curve is really high, and here the conduction domain, which is more more precise. So yes, so to conclude, we made some laser analysis that underline really high focal shift, but it's not measured and validated experimentally. This is a reassuring result because if we are actually this high focal shift, it will be impossible to construct with this machine that is not observed because other people use this without have any problem. But we have a focal shift, and we're actually working on to better measurement this focal shift. So by new laser analysis and sample fabrication. We also try to construct some surface and volume sample in keyhole regime in order to better understand the different interaction, not only by construct a single tract, but many single tracks successive and layer on the layer to understand different interaction, and continue to develop the normalized enthalpy model with more data and from me and from literature. Thank you.